Hello class, and welcome back to our videos on rotational kinematics. In this video, we are going to focus on our next kinematics quantity, which is going to be angular velocity. As a reminder, in this video module, our big goal is to develop the language and the basic equations and variables that we need to properly describe the motion of objects as they are rotating. So we have already covered rotational displacement, and in this video we are going to focus on rotational velocity. How fast are objects spinning? Objects can be spinning at a slow rate or a fast rate, so we are going to look at the language, variables, and equations we can use to describe the differences between these two rotational motions. Again, I'm going to introduce you to some new variables and units, so be sure to make notes of these new symbols. So while angular velocity is going to be a new term, the idea of velocity should not be new. We have already looked at the velocity of different objects. So we would describe both this red and this blue object as being in translational motion. Their position in space is changing, but we would definitely describe them as having different velocities. As a reminder, for translational motion, velocity was how many meters the object covered each second and in which direction. So this blue object has a very high velocity because it's covering about 18 meters each second, but this red object has a pretty slow velocity. It seems to only be covering about 6 meters each second. Velocity was how many meters the object was covering per unit time. And of course, we also had a direction associated with velocity, so both of these objects have a positive velocity. Angular velocity is going to be a similar quantity. Angular velocity is a term that describes how fast an object is spinning, or more specifically, how many radians it rotates through each second. As something is rotating, if it is covering more radians each second, it is going to be spinning with a higher angular velocity. So these two spinning objects that I have shown here on the right, visually it's probably pretty clear to tell that the object on the bottom is spinning at a faster rate than the object at the top. But if we start to really pick apart what it means to have a faster angular velocity, we really need to look at how many radians the object is going to cover in 1 second. So what I'm going to do is let these objects rotate for exactly 1 second, and let's see how many radians they cover. So this top object seemed to have an angular displacement of approximately pi over 4 radians. As a reminder, the whole circle is 2 pi, half of a circle is pi, so this seems to be about a quarter of half of a circle, which is going to give us pi over 4 radians in 1 second. So we've seen to go about pi over 4 radians each second. This object at the bottom was spinning faster. It seems to have gone pi radians in 1 second, or would have an angular velocity of pi radians per second. Notice this object at the bottom has 4 times this angular velocity as the object at the top, and we can definitely see that it is visually spinning about 4 times as fast. So one thing to note about angular velocity is that angular velocity is dependent on angular displacement, which really is how far around the circle the object has traveled, not a linear distance that the object has traveled. So if we look at both of these two rotating objects, notice these two objects have different sizes. One of them is very long and one of them is very short. Visually, it might appear that the object on the left is moving a lot faster because it is a lot longer, but notice their rate at which they are completing their circular paths are exactly the same. Both of these objects have the same angular velocity. The size of the circle does not matter, whether it's a big rotation or a small rotation. It's just how quickly you are covering the 2 pi radians of this circle. So don't be tricked by objects of bigger sizes. Angular velocity is going to be the same for both of these objects. So if we want to represent angular velocity in equations, we need a symbol or a variable for that. lowercase v already represents linear velocity, so we need a new value. The symbol we're going to use for angular velocity is going to be a lowercase Greek letter omega. So the omega might be a new symbol for you, but it is a Greek letter. We're going to call it omega. When we see this symbol, it is right here. It might look like a W, but it is not a W. Usually W's are made up of straight lines. Even if you have fancy handwriting and you draw your W's a little bit curvy, keep in mind this is not a W. Do not call it a W. It is an Greek letter omega. Don't call it a W, and definitely do not write it in this straight line way. We are going to draw it like this. So, might seem a little cheesy, but I've given you an opportunity to practice drawing an omega. So we're gonna go all the way back to kindergarten. What I want you to do, trace these omega symbols. Get used to these two curves to show this Greek letter. Again, similar to a W, but definitely not a W. So practice it 4 times on your own, and then keep going just like we are in kindergarten. If I see this symbol and I'm not entirely sure if it's an omega or not, I'm going to assume it isn't. Make sure you are forming this symbol correctly. So symbol for angular velocity is this Greek letter omega. And we saw a couple of moments ago that the angular velocity is going to be how many radians you cover per second. So the SI unit that we are going to use is going to be the radian per second. So the calculations for angular velocity are going to be pretty intuitive, how many radians you cover per second, but we do have a written out formula for this quantity. And just as a reminder, one of the very first physics formulas we learned was our equation for linear velocity. Linear velocity is displacement over time. Or more specifically, as long as the object is moving at a constant velocity, then the velocity was displacement over time. This was our model for motion at a constant velocity. Keep that in mind. There is a similar equation for the angular version. Again, as long as this object is moving at a constant angular velocity, which means it covers the exact same number of radians each and every second, then the angular velocity of the object is going to be its angular displacement divided by time. This is just a direct translation from our linear quantities to our angular quantities. Instead of linear velocity, we have angular velocity, omega, and instead of linear displacement, we have angular displacement, theta. Notice there is no angular version of time. Time is not dimensional, so it's just going to be the exact same variable. Now notice, 2 things that I've underlined. These 2 equations only work when you are moving at a constant velocity. It's getting its own slide, its background is yellow, so that you know. Please notice this, please highlight it, circle it. This equation is only to be used when the object is moving at a constant angular velocity. That means it is not accelerating. It is not speeding up, it is not slowing down. Once it begins to accelerate, we need our new set of equations. We need our acceleration equations. This equation does not take into account acceleration. So honestly, you're rarely going to be using this equation because most of our objects are going to be accelerating. So please, please, please do not overuse this equation. It only applies to a very specific situation, constant angular velocity. But if we know or can assume the object is moving at a constant angular velocity, we can use that equation. So let's just look at 2 quick examples of ways that we can use this equation. Now, the math itself for these examples are not going to be all that difficult. Big thing I really want us to pay attention to as we're going through these examples are the units. As a reminder, for angular motion, we need our units to be in radians per second. So in this first example, we have a wheel that is making 12 full revolutions, notice, weird unit, in 1 minute. Another weird unit. What is the angular velocity of the wheel? So since acceleration is not mentioned, we are going to assume it is moving at a constant angular velocity omega the whole time, and that's going to be its angular displacement over time. Now you might be tempted to just do 12 divided by 1 to give us 12 revolutions in a minute. While that is an angular velocity, it's not in our correct SI unit, so we need to do some conversions. 12 full revolutions is also going to be 12 times 2 pi radians, which is going to be 24 pi radians. So our angular displacement is going to be 12 times around the circle, or 24 pi. Our time, 1 minute, is actually going to be 60 seconds. So notice some pretty basic unit conversions, but just be on the lookout. Revolutions and minutes do show up. Make sure you are converting to radians and seconds. So once I plug this into my calculator, I will get 1.26 radians per second, correct unit, so I am good. Feel free to use either the pi button on your calculator or the value 3.14. There is no preference to which one you use, but please do not leave this in terms of pi. You might be tempted to just simplify this to 2/5 pi radians per second, but this has no meaning. I have no idea what 2/5 of pi is, but I definitely know what 1.26 is. So make sure in physics you're always giving me a real value in decimals. Avoid keeping it in terms of fractions and especially constants like pi. So try this next one on your own, and then when you unpause the video, I will show you the solution. So a merry-go-round is spinning at a constant angular velocity of 2 radians per second. How long will it take this merry-go-round to make 4 complete revolutions? So since this is constant angular velocity, we can definitely use our equation. The angular velocity omega is going to be equal to the angular displacement divided by time. And we are looking for the time. So we know the angular velocity is going to be 2 radians per second, and we just need to figure out the angular displacement so we can solve for time. Now, 4 complete revolutions is not in the correct unit because our angular velocity is in radians. So 4 complete revolutions is actually going to be 4 times 2 pi radians. So 2 radians per second is going to be equal to 8 pi radians divided by how many seconds? Now from here, we can do this in our head, but you can also just do the algebra, but we're going to end up with our time being equal to 4 pi seconds. But please do not leave this in this form. If your coach tells you you have 4 pi seconds to get this move done, you have no idea what that means. So please multiply 4 times 3.14 to get me a true time, which is going to be 12.56 seconds. Again, with these kinematics quantities, just really be on the lookout for units. Make sure everything ends up in radians and seconds. So, in summary, angular velocity is going to be how many radians an object has rotated through each and every second. So if we look at this GIF here that was in the introduction of this video, this fan is spinning at an angular velocity, so is the string, and so is the cat. For the most part, they are all spinning at the same angular velocity. They seem to be making a full turn in the same amount of time. The symbol that we are going to use for angular velocity is the Greek letter omega. Definitely get used to hearing and saying that symbol and also writing it. And the unit is going to be the radian per second. And as a reminder, as long as the object is moving at a constant velocity, we can calculate the angular velocity of that object using this equation here.